Using principle of mathematical induction, we can prove the statements P of n for all n belonging to capital N. This method involves two steps. The first one is the basic step. In this basic step, we prove that P of 1 is true. Then the second step is the induction step. In this step, we assume that P of k is true. Assume that P of k is true. And using this P of k result, we prove that P of k plus 1 is true. So to prove P of k plus 1 is true, we use P of k step. So we are inducing the result that P of n is true for all values of n. These two steps establish the statement P of n for all n belonging to capital N. Let us do exercise 4.1. First question. The given statement we denote it as P of n, which is 1 plus 3 plus 3 square plus etc. The nth term is 3 power n minus 1, which is equal to 3 power n minus 1 divided by 2. Now our first step is we have to show that P of 1 is true. This is a series. Series means sum of the numbers of a sequence. So this has n terms. P of n has n terms. So P of 1 will have only one term. The first term, which is 1, is equal to, substitute n as 1 on the other side. So we get 2 by 2, which is 1. Therefore, P of 1 is true. So if P of 1 is true, we proceed to do the induction step. If this is not true, we can say that the statement cannot be proved. Okay, the next step is let P of k be true. Let us write P of k statement, which is 1 plus 3 square etc. Kth term is 3 power k minus 1, which is 3 power k minus 1 divided by 2. Now to prove. So this is the statement we are going to prove. P of k plus 1 statement. P of k plus 1 statement will have k plus 1 terms. I am writing the kth term, and k plus 1th term will be, in this last term we have to substitute n as k plus 1. So it becomes k plus 1 minus 1, which is 3 power k. Now similarly here we will substitute n as k plus 1. So 3 power k plus 1 minus 1 divided by 2. Let us prove this result using P of k result. Always remember, to prove P of k plus 1, we have to make use of P of k. Now for the first k terms, we know the total. So LHS is equal to, it becomes 3 power k minus 1 by 2, and this term I have to write, which is 3 power k. This step is using P of k. I'll write by P of k, which is equal to, take LCM 2. It becomes 2 times 3 power k. These two are like terms. This and this. Let us add them. it becomes 3 times 3 power k divided by 2. Add the exponents. 3 power 1 into 3 power k becomes 3 power k plus 1 minus 1 divided by 2. And we got the right hand side. Therefore, we have to write the conclusion step. P of k plus 1 is true whenever P of k is true. Because using P of k only we could prove P of k plus 1 to be true. Therefore, we conclude that the given statement P of n is true for all n belonging to the natural number set n. Let's do question number 2. The given statement P of n is 1 cube plus 2 cube plus 3 cube, etc. and the nth term is n cube equal to n into n plus 1 divided by 2 the whole square. The basic step is proving P of 1 to be true. Let us do that step. P of 1 will have only one term. P of n has n terms. So P of 1 has one term, which is the first term, equal to, on the other side, substitute n as 1. 1 plus 1 is 2, divided by 2 the whole square. So 1 is equal to 1. Therefore, P of 1 is true. Let P of k be true. This is our induction step. I am writing P of k statement, which is 1 cube plus 2 cube plus 3 cube, etc. The last term will be k cube. This is the kth term, and which is equal to, substitute n as k. K times k plus 1 by 2 the whole square. Now to prove, we are going to prove P of k plus 1 statement, and the statement is 1 cube plus 2 cube plus 3 cube, etc. Let us write the kth term, which is k cube, and then the last term is k plus 1th term, which is k plus 1 the whole cube, is equal to, the right hand side we will substitute n as k plus 1 here. So it is k plus 1. K plus 1 will be k plus 2 by 2 the whole square. This is the result which we have to prove. Now if you see the left hand side, for the first k terms we know the total by P of k. So let us make use of P of k statement to prove P of k plus 1 statement. So the left hand side becomes, for the first k terms, I can write this, and then k plus 1th term is k plus 1 the whole cube. I am distributing this power 2. And plus k plus 1 the whole cube. Take out the common factors. K plus 1 the whole square is a common factor. We get k square by 4 plus k plus 1 from the second term. Let us take LCM. We get k square plus 4 times k plus 1, which is 4k plus 4 divided by 4. And this is k plus 1 the whole square. K square plus 4k plus 4 is the expansion of k plus 2 the whole square by 4, which can be written as k plus 1 into k plus 2 divided by 2 the whole square. And this is the right hand side of P of k plus 1 statement. We have proved. So let us write the conclusion. Therefore, P of k plus 1 is true whenever P of k is true. Therefore, we conclude that P of n, the given statement P of n is true for all values of n belonging to capital N. Question number 3. Let us take the given statement as P of n, which is 1 plus 1 by 1 plus 2, and the third term is 1 by 1 plus 2 plus 3 plus etc. Nth term is 1 divided by 1 plus 2 plus 3 etc. up to n equal to 2n over n plus 1. P of 1 statement will have only the first term, 1. Now n is 1 on the other side, so 2 into 1 divided by 1 plus 1. We get 1 is equal to 1. Therefore, we can conclude that P of 1 is true. The basic step is true. Now we assume, in induction step, we assume that P of k is true. And write P of k statement. P of k statement will have k terms on the left hand side. And the third term is this. I am writing the kth term, 1 plus 2 plus 3 etc. up to k. This is the kth term, equal to the other side, put n as k. Now to prove, let us write P of k plus 1 statement. Which is 1, 1 by 1 plus 2, second term, third term, etc. I am writing kth term, 1 plus 2 plus 3 plus up to k. This is the kth term. And now k plus 1th term, 1 plus 2 plus 3 etc. up to k plus 1. And we have to show that this is equal to 2 times. Here substitute n as k plus 1. So 2 times k plus 1 divided by k plus 1 plus 1, which becomes k plus 2. Now let us take the left hand side. So for the first k terms, the total is this by P of k. Therefore, I am replacing the first k terms by this total, 2k by k plus 1. And now write k plus 1th term, which is 1 plus 2 plus 3 etc. up to k plus 1. This step is by P of k. And this is an AP. Now sum up to n terms of an AP is n by 2 times A plus L. Or we may use n by 2, 2a plus n minus 1 times D. Or we may use some special sequence formula also. 2k by k plus 1. Let us use AP formula. In this we have n, k plus 1 terms we have. So n is k plus 1. K plus 1 by 2 into A is the first term and L is the last term. Last term is k plus 1. Let us simplify this. 2 divided by k plus 1 into k plus 2. Now take out the common factors. Here the common factor is 2 in the numerator and k plus 1 in the denominator. We have k in the first term and 1 by k plus 2 in the second term. Let us take LCM k plus 2. K times k plus 2 becomes k square plus 2k and plus 1. 2 divided by k plus 1 into k square plus 2k plus 1 can be written as k plus 1 the whole square divided by k plus 2. So one factor we can cancel and we get the right hand side. 2 times k plus 1 divided by k plus 2. And this is the right hand side. Therefore, p of k plus 1 is true. But remember, we have proved p of k plus 1 assuming that p of k is true. So you have to write that p of k plus 1 is true whenever p of k is true. Therefore, p of n is true for all n belonging to capital N. Now fourth question. The given statement is p of n, which is 1 into 2 into 3 plus 2 into 3 into 4 plus etc. n into n plus 1 into n plus 2 equal to n into n plus 1 into n plus 2 into n plus 3 divided by 4. The first step, proving p of 1 is true. So p of 1 will have only the first term equal to n is 1 here, 1, 1 plus 1 is 2, 1 plus 2 is 3, 1 plus 3 is 4 divided by 4. We get 6 equals 6. Therefore, p of 1 is true. This is our basic step for induction method. Now we will do induction step. In that we first assume that p of k is true. And write p of k statement, which is 1 into 2 into 3 plus 2 into 3 into 4, etc. Kth term is k into k plus 1 into k plus 2, which is equal to, substitute n as k in the given statement, k plus 2, k plus 3 divided by 4. This is our p of k statement. Now to prove, this is the result to be proved, which is the statement p of k plus 1. 1 into 2 into 3 plus 2 into 3 into 4 plus etc. I am writing the kth term. Now let us write k plus 1th term. For k plus 1th term, put n as k plus 1 in that step. So first one is n, which is k plus 1. And then second one is n plus 1. K plus 1 plus 1. N is k plus 1. So it becomes k plus 2. And then n plus 2 becomes k plus 1 plus 2, which is k plus 3. Equal to, now we have to substitute k plus 1 for n here in this step. It becomes k plus 1 times k plus 2 times k plus 3 and last term is k plus 4 divided by 4. Now in p of k plus 1, look at the first k terms. It is same as p of k, left hand side of p of k. So we can replace it by the right hand side of p of k. So LHS of this is equal to, use p of k. So it becomes k into k plus 1 into k plus 2 into k plus 3 divided by 4 plus k plus 1th term I have to write, which is k plus 1 into k plus 2 into k plus 3. Take out the common factors. K plus 1, k plus 2, k plus 3 are common factors. We have k by 4 from the first term and 1 from the second term. Take LCM for the last term. 4 is the LCM. We get k plus 4. And this is k plus 1 into k plus 2 into k plus 3 into k plus 4, whole thing divided by 4. And this is the right hand side of p of k plus 1 statement. So we have proved that p of k plus 1 is true. We will write the conclusion step. Therefore, p of k plus 1 is true whenever p of k is true. Therefore, the given statement p of n is true for all natural numbers. That's it. Now question 5. P of n, the given statement is 1 into 3 plus 2 into 3 square, 3 into 3 cube, etc. n into 3 power n is equal to 2n minus 1 into 3 power n plus 1 plus 3 divided by 4. So p of 1, here in p of n, this left hand side has n terms, but p of 1 will have only the first term, only one term. Equal to n is 1, 2 minus 1 is 1, into 3 power 1 plus 1 square, it becomes plus 3 by 4. This is 9, 9 plus 3, 12 by 4. So we get 3 equals 3. Therefore, p of 1 is true. Now the next step, we assume that p of k is true. And write p of k statement, which is 1 into 3 plus 2 into 3 square plus 3 into 3 cube plus etc. Kth term is k times 3 power k equal to, replace n by k, 2k minus 1, 3 power k plus 1 plus 3 divided by 4. Now to prove, we are going to prove p of k plus 1 statement, which is 1 into 3 plus 2 into 3 square, etc. Kth term is k into 3 power k, And now k plus 1th term, k plus 1 3 times k plus 1. That is, in place of n, we have to substitute k plus 1 for p of k plus 1 statement. Similarly, here also for n, we substitute k plus 1. 2n minus 1 will become 2 times k plus 1 minus 1. So it becomes 2k. 2 minus 1. 2 minus 1 is plus 1. And 3 power k plus 1 will give you k plus 2 plus 3 divided by 4. Okay, now let us prove p of k plus 1 using p of k result. So for the first k terms, I can use this total. So the left hand side is equal to 2k minus 1 times 3 power k plus 1 plus 3 divided by 4 using p of k result. And the last term, k plus 1th term, is this term I have written. So this is by p of k. Now let us simplify this by taking LCM 4. 2k minus 1 times 3 power k plus 1 plus 3, and this is 4k plus 4 times 3 power k plus 1. I have taken LCM 4, so I need to multiply the second term by 4. Now 3 power k plus 1 is a common term, so we get 2k minus 1 from the first term and 4k plus 4 from the last term, and the middle term is 3 divided by 4. So we get 6k plus 3 into 3 power k plus 1 plus 3 by 4. Here in this 6k plus 3, 3 is common. Let us take 3 out. We get 2k plus 1 into 3 into 3 power k plus 1 and plus 3. So these two we can combine. Here the power is 1 for the first 3. For the next 3, it is power is k plus 1. Add the exponents. It becomes k plus 1, which is k plus 2, plus 3 divided by 4. This is the right hand side of p of k plus 1 statement. That's it, we have proved. Write the conclusion. Don't forget to write the conclusion steps for all induction questions. Therefore, p of k plus 1 is true whenever p of k is true. Therefore, the given statement p of n is true for all natural numbers. Question 6. P of n is the given statement 1 into 2 plus 2 into 3 plus 3 into 4, etc. n into n plus 1 is equal to, the right hand side is n into n plus 1 into n plus 2 divided by 3. This has n terms. P of n statement has n terms, but P of 1 will have only one term, the first term 1 into 2, equal to, substitute n as 1. 1 plus 1, 1 plus 2 is 3, divided by 3. So we get 2 equals 2. Therefore, the P of 1 statement is true. Now let P of k be true. P of k statement is 1 into 2 plus 2 into 3, etc. K into k plus 1 equal to, replace n by k. Here, k times k plus 1 times k plus 2 divided by 3. Now to prove, we are going to prove P of k plus 1 statement. Which is 1 into 2 plus 2 into 3, etc. Kth term is k into k plus 1. And k plus 1 term will be k plus 1 into k plus 1 will become k plus 2 equal to, now on the right hand side of P of n statement, so substitute n as k plus 1, k plus 1 plus 1 is k plus 2, k plus 1 plus 2 will become k plus 3 divided by 3. Now take the left hand side of this and we can replace the first k terms by P of k total. P of k total is this. Therefore, it becomes k times k plus 1 times k plus 2 divided by 3 plus k plus 1th term I am copying. Take out the common factors. The common factors are k plus 1 and k plus 2. So the first term becomes k by 3 and the second term is 1. Let's take LCM. And we get the right hand side. The simplification is so easy. Therefore, P of k plus 1 is true. Whenever P of k is true, therefore P of n is true for all small n belonging to capital N. Now question 7. P of n statement is 1 into 3 plus 3 into 5 plus 5 into 7, etc. And the nth term is 2n minus 1 times 2n plus 1. And it is equal to n into 4n square plus 6n minus 1 divided by 3. Okay, P of 1 will have only the first term. Remember that. Equal to, plug in the value 1 for n, 1, 4 plus 6 minus 1 divided by 3. 1 into 3 is 3. Here 10 minus 1, 9 by 3 is also 3. Therefore, P of 1 is true. Okay, now the next step, let P of k be true. Write P of k statement, which is 1 into 3 plus 3 into 5 plus etc. 2k minus 1 times 2k plus 1 equal to n is k here, 4k square, that is k times 4k square plus 6k minus 1 divided by 3. Now let us write the result to be proved, which is p of k plus 1 statement. 1 into 3 plus 3 into 5 plus 5 into 7, etc. Kth term is 2k minus 1 into 2k plus 1, and we have to write k plus 1th term. The nth term is this. Now replace n by k plus 1. So 2 times k plus 1 minus 1, and here 2 times k plus 1 plus 1. If you simplify, 2 minus 1 becomes 1. Here 2k, this is 2 plus 1, which becomes 3. So our k plus 1th term is 2k plus 1 times 2k plus 3. Which is equal to, now we write the right hand side by substituting n as k plus 1. It becomes 4 times k plus 1 the whole square, 6 times k plus 1 minus 1 divided by 3. This is the result to be proved. Okay, but bringing the result to this form will be little difficult. So we will expand and simplify the result, and that result we will get. So I am simplifying this result to be proved. So k plus 1, let us expand. It becomes k square plus 2k plus 1. And this is 6k plus 6 minus 1 divided by 3. Four k square, and here we have, okay, let me expand and write 8k plus 4, 6k plus 6, 6 minus 1 is 5 divided by 3. K plus 1 times, let us add the like terms and write 8k plus 6k, which will be 14k, and 4 plus 5 is 9, plus 9 divided by 3. We will further simplify this result. Open the brackets, 4k cube, so that we can avoid factorization. Otherwise you have to factorize and show this result. So remember, simplify here itself, so it will be easy for us to prove the simplified step instead of doing factorization. That too, factorization of a cubic expression, so we can avoid. This is equal to 4k cube and 14k square plus 4k square. Here these two are like terms. 18k square, and here we have 9k and 14k, which is 23k plus 9 divided by 3. So we will prove this result, which is easy for us to prove to avoid factorization. Now let us take the left hand side of the result to be proved. I am writing the left hand side plus etc. Kth term is 2k minus 1 into 2k plus 1, and k plus 1th term is 2k plus 1 into 2k plus 3 equal to, now for the first k terms we know the total by p of k. Let us write the total of p of k, that is sum of first k terms is this, 4k square plus 6k minus 1 divided by 3 plus the last term, which is 2k plus 1 times 2k plus 3. Let us take LCM 3. Open the brackets and write 4k cube plus 6k square minus k, and 3 times this because we are taking LCM, which is 4k square plus 6k plus 2k, and 1 into 3 is 3. 4k cube, 6k square minus k, 3 4s are 12. This total is 8k. 8 3s are 24k and 3 3s are 9. Divided by 3. Add the like terms and write. We have 6k square and plus 12k square, which is 18k square. And k terms, we have minus k plus 24k, which is plus 23k, and the constant term is plus 9 by 3. We get the right hand side. Therefore, P of k plus 1 is true. Whenever P of k is true, because we have used P of k result to prove P of k plus 1 result. That's why we write whenever P of k is true. Therefore, we conclude that the given statement P of n is true for all n belonging
Thank you for
to
watching, and
the
please
natural
subscribe
number
the
set
channel.
n.